All right, guys, so in this video, we're going to be starting off by talking about section 10.1, okay? So section 10.1 primarily covers estimating a population mean, all right? First thing we're going to look at is how much does an Oreo weigh? So it says Mrs. Gaulis wants to estimate the average weight of an Oreo cookie to determine if the average weight was less than advertised. She selected a random sample of 30 cookies and found the weight of each cookie in grams. The mean weight was 11.1921 grams with a standard deviation of 0.0817. It says make a 95% confidence interval to estimate the true mean weight of an Oreo. So what is our point estimate for the true mean? So we don't know what the true mean is, but our best guess is our point estimate, right? And so she sampled 30 cookies randomly and found a mean weight of 11.1921, okay? So this is our best estimate, it's our point estimate on what the true weight of these Oreos are. And now the population, she's wanting to make an estimation for all Oreos, okay? All Oreos. Our sample, all right, so she randomly sampled 30 Oreos that were selected, okay, so 30 Oreos. Our parameter, all right, what are we trying to measure here? Well, we're trying to measure mu, which represents the true mean weight of all Oreos. And then our statistic. So our statistic is just the value that we use to represent that true mean mu, which again is just 11.1921. Now, number 3 says, was the sample random? Why is this important? So it originally told us that she had a random sample of 30 cookies. So yes, it was random. And this is important because it helps us generalize for the population. All right, so this is important because it helps generalize for the population. All right, so at the end of this study, or at the end of this test, excuse me, whatever results we find, if we find they're statistically significant, we can say that that's statistically significant for all Oreos, for the entire population. And so when you're doing this type of test, you just got to remember your conditions. So this is condition number 1. Okay, you have to show that it's random. All right, next one, number 4, it says, what is the formula for calculating the standard deviation of the sampling distribution of X bar? So normally, if you're trying to calculate the standard deviation, we're going to have population standard deviation over the square root of n, okay? Now, number 5 says, what condition must be met to use this formula, and has it been met? So this is the 10% rule, or the 10% condition. All right, has this been met? Yes. All right, we know that because our sample is less than 10% of the population. So if we plug in our numbers, she took a random sample of 30, which is definitely less than 10% of all Oreos. Okay, so this is condition number 2. Okay, 10% rule. So you got to check this condition as well. Same type of conditions we've been using, okay? And then number 6 says, in the formula for standard deviation, the sampling distribution of X bar, we don't know the value of sigma, all right? If we did, we would have known what the true value was. So we're going to use S sub X instead. And so this is known as the standard error. Okay, so the standard error of X bar. Instead of sigma, okay, the standard deviation for the population, we're actually using S sub x. It's the standard deviation of the sample. So we got S sub x over square root of n. So we're going to have 0.0817 over the square root of 30, which gives us 0.0149. Now, would it be appropriate to use a normal distribution to model the sampling distribution of x bar? Justify your answer. All right. So the answer would be yes. And if you look, our sample was 30. Okay. And if you remember, if our sample is greater than or equal to 30, then we're okay. All right. So remember, if your sample is greater than or equal to 30, then you're good. All right, this is known as the central limit theorem. Or CLT for short. It doesn't really matter if your population is skewed, okay? If your distribution, or if your sample is 30 or larger, then that means that typically your distribution is going to show a normal distribution. So this is going to be condition number 3. Okay, this is our normal / large counts. Okay. Number 8 says, when finding the margin of error for a confidence interval for a proportion, we use Z star. Now, for a mean, what we're going to do is we're going to use T star as a critical value. And you might be wondering why. So first I want to tell you T. Instead of looking at Z, we're going to look at T. This is represented as x bar minus mu, whatever your supposed mu is. In this case, they tell us that Oreos should weigh where is it? Actually, it's down below. It's a little bit later. Now, x bar minus mu divided by our standard error, so S sub x over root n. And the reason we do this, okay, if I drew a graph like this would be a normal curve, kind of like this. So this is our normal curve. A T distribution is a little bit more spread out. It's a little bit more spread out than a normal distribution. Okay, so this is a T distribution. Okay, and we use a T distribution because we don't know what mu, or what our population mean or standard deviation are. Okay, so we use T because we don't know what mu or sigma are. All right. So we're going to need a wider spread in order to accommodate for that. All right. So we need a wider spread for a critical value. All right, now it says what is T star, or what T star is needed for this confidence interval? Use table B and the degrees of freedom, or DF, equals n minus 1 to find it. So in order to find T star, we need to know what our critical value is. Or excuse me, our degrees of freedom are, okay? So degrees of freedom, like it says, DF, is always just equal to your sample size minus 1. So in this case, our sample size was 30. So our degrees of freedom is going to be 29. Now, you could use table B, or a quicker way you could do this If you have a TI-84 or TI-83 calculator, you can do inverse T. And on the inside, you're going to have two numbers. You're going to have your tail and your degrees of freedom. Okay, so whatever your tail is and your degrees of freedom. We already know our degrees of freedom is 29 here, okay, for this one. And now for your tail, so for example, if we are doing a 95% confidence interval, okay, so a 95% confidence interval, here is 95% of your data. That means that each one of these tails are worth 2.5%. Okay. So these tails are worth 2.5% each. So that means as a decimal, your tail is worth 0.025. So whatever your tail value is, just put it as a decimal and then your degrees of freedom. So if I were to plug this into my calculator, I'm going to get a T-star of 2.045. Okay, so T-star in this case is 2.045. All right, now it says calculate your margin of error using T-star and the standard error. Okay, so margin of error is equal to your critical value times your standard error. If I were to write that in actual value or symbols, it'd be T-star times SX over root N. So we already calculated T-star is 2.045. Our standard error was 0.0149. So that means our margin of error is going to be, in this case, 0.0305. Okay. And now it says calculate the 95% confidence interval using point estimate plus or minus margin of error. Okay. So again, same exact formula we've been using. Confidence interval is point estimate plus or minus our margin of error. So if I were to write out the actual formula, we would have X bar plus or minus T star times SX over root N. And so we're going to have 11.1921 plus or minus 0.0305 for a confidence interval from 11.1616 up to 11.2226. All right, now it says interpret this interval. Okay, so since we're doing a 95% confidence interval, we're going to say we are 95% confident the interval from 11.1616 to 11.2226 captures the true mean weight and in parentheses I'm going to put in grams. Make sure that you specify a unit, okay? So in this case, we're talking about grams, so I want to put that somewhere in it. True mean weight in grams of all Oreos. And now it says write a specific formula. We already did that, but we'll just go ahead and write it again. Our confidence interval is equal to X bar plus or minus T star times SX over root N. And now it says, according to Nabisco, an Oreo weighs 11.3 grams. Does our confidence interval provide convincing evidence that the true mean weight is less than 11.3 grams? And explain. So our confidence interval was from 11.1616 to 11.2226. And now Nabisco is saying that the true mean weight is 11.3, which is way up here. All right? So our confidence interval does not contain 11.3. Our entire interval is below 11.3. So what that tells us is that we do have, based on our confidence interval, we have convincing evidence that it is less than that. All right? So we're going to say yes. Our entire interval is below 11.3 grams. Okay? Which tells us that it is unlikely for an Oreo to weigh that much. Okay. All right. So as a recap, these are bullet points number 1 and 2 on the front of your packet. Number 1 is critical values. Okay, so T-star. We use this for estimating means. So use for estimating means. Something else you'll need are your degrees of freedom. Okay, so df is always equal to n minus 1. And now you can use table B, or you can use inverse T, where first number is your tail, and then you have your degrees of freedom. Okay. And then bullet point number 2 are your conditions. Okay. So you need to show that it's random. Okay. So you need to show that it's a random sample or assignment. You need to do 10% rule. Okay, so your sample needs to be less than 10% of your population. And then you need to do normal or large sample. Okay, so when you're doing the normal or large counts, there's one of 3 ways you can do it. You can show that the population distribution is approximately normal. Okay, and it might say this in the problem itself. It might tell you that this data comes from a normally distributed population. If it says that, all you got to do on that section is just say states population distribution is approximately normal. Done. Another way you could do it is to show that your sample is greater than or larger to 30. This would be your central limit theorem. Or you can show that the sample data shows no strong skewness or outliers. Okay. you can just choose one of these. The first one is obviously the easiest. It'll just tell you if it's approximately normally distributed. Next easiest would be central limit theorem. And then if neither of those hold up, then you'll just have to show that the sample data shows no strong skewness or outliers. The best way to do that is to graph the data, make like a dot plot or something like that, and show the distribution is approximately normal. All right, so I'm gonna leave the check your understanding for you. Key is on here if you need to check yourself. But we're gonna go ahead and move on to the next part. It says, how many states can you name? So this is the last thing for section 10.1. It says, how many states can you name in 1 minute? We will use this class as a random sample of AP Stat students to estimate a 95% confidence interval for the mean number of states an AP Stat students can name in 1 minute. So unfortunately, we don't have a physical classroom, so we can't pull our data together. But I will give you some sample data just for the sake of this lesson. If you would like to test yourself, feel free to pause, put a 1 minute timer on your phone or something like that, and see how many states you can name. So it says, when the timer starts, list as many states as you can in one piece of paper. Write down the number of states you listed on the board. What type of data is this, categorical or quantitative? So this would be quantitative data. Because it's numbers. All right, this is something that we can have numbers with. Think of quantitative data as data that you could average together. You could find an average for, right? It would make sense to see on average how many students could name, how many states students can name in 1 minute, right? You just got to be careful with something like with categorical data. So some categorical data can be represented as numbers. For instance, if you're compiling a list of zip codes, it would not make sense to average zip codes together because those represent physical places, right? But in this case, we're looking at quantitative data. So as a class, let's just say, for example, we had 32 students, so 32 pieces of data. The average number of states students could name, I had this from another class, it was 16.813, standard deviation of 5.527. All right, so it says construct a 95% confidence interval to estimate the mean number of states a senior can name. So if we were doing a 4-step process like this, first part, I need to know the parameter and the confidence level. So our parameter, mu, represents the true mean number of states an AP Stat student can name in 1 minute. Okay, and then our confidence level, we're just going to stick with 95%. Okay. In the plan section, I need to know the name of the procedure, and then I got to check my conditions. So we have one sample, and we are doing a confidence interval, right? So the name of the procedure is one sample. And since we're doing means, it's going to be a t interval for mu. All right, so conditions. Random, all right? So it's assumed that it was random, right? Y'all were put into my class randomly, right? And so we don't know. I didn't handpick you to be put in my class, so this is a random sample of 32 students. Next up, we got his 10% rule. Okay, so our sample has to be less than 10% of the population, so it's safe to assume that 32 is less than 10% of all AP Stat students. And then last thing is normal. Okay, it's safe to assume that it's normal because n is greater than or equal to 30, which we have. 32 is greater than or equal to 30. This is a central limit theorem. So we got all our conditions met. And so now we can move on to the do section. So first off, general formula. Remember, we've got confidence interval is equal to point estimate plus or minus our margin of error. Okay. The specific formula, remember we've got x bar plus or minus t star times sx over root n. And so if I put all of my data in there for this, I'm going to get 16.813 plus or minus t star in this case is 2.042. I'll show you that here in a second. Over standard deviation of 5.527 divided by the square root of 32. So I'm going to get 16.813 plus or minus 1.995 for a confidence interval of 14.818 up to 18.808. And so remember, in order to get t star, this is a little side note, that's equal to inverse t. My tail, since I'm doing a 95% confidence interval, my tail is 0.025. And my degrees of freedom, I had 32 people, so my degrees of freedom will be one less than that, which is 31. And we got 2.042. Okay, so here's my confidence interval. And now it's asking me to interpret the interval in context of the problem. So I just say we are 95% confident. The interval from 14.818 to 18.808 captures the true mean number of states an AP Stat student can name in 1 minute. Okay. And so important ideas. So this is number 3 on your bullet points. So this will be our construct and interpret. So basically our 4-step process. Okay, so in the state section, you need to tell me your parameter and your confidence level. In the plan section, you need to tell me the name of the procedure and your conditions. In the do section, you need to tell me general and specific formulas. You need to show me your work. You need to show me what T-star is and your degrees of freedom. And you need to show me your final answer. And then in the conclude, you just need to interpret in context. And so that's where you say we are 95% confident, blah, blah, blah. Okay? All right. So check your understanding. I'm going to leave to y'all. Okay? Again, you can check your work with the answer key. But in the next video, we will go over section 10.2.